This is the first of probably about 6 or 7 calculus problem solving videos focused on computing derivatives. We start with something called the Power Rule, Linearity of Derivatives, and we apply those ideas also to polynomial derivatives. The first couple problems involve the limit definition of the derivative, but after that point we avoid limits. Number 1 says let f of x be x to the n power. That's called a power function. X is the variable, n is fixed. It is a fixed number like 2 or 3 or 4. In fact, it is a positive integer, 1, 2, 3, 4, 5, 6, etc. It's not a fraction. It's not a decimal. It's not an irrational number like pi. It's not a negative number here. We can derive the power rule in those situations, but it's harder. This is the easiest kind of situation. We want to use the definition of the derivative to compute the derivative, f prime of x. A little bit of extra directions. Your calculation is going to involve unspecified higher order terms, HOT, or hot for short, that we do need to know a little bit about the binomial theorem to specify them a little bit, but we won't say completely what they are. We won't talk about the binomial theorem in its full generality. So let's go to the limit definition of the derivative. F prime of x, by definition, is the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. When you do this calculation, you think of x as fixed and h is the variable that's going to 0. These fractions right here are called difference quotients. They represent slopes of secant lines. And this limit, if it exists, is then by definition the slope of the so-called tangent line to the graph of f of x at that value of x. Go ahead and use the function. The function is x to the n power. So we need to compute here f of x plus h. That means x plus h quantity to the n power. And then we need to subtract f of x, which is x to the n power, and divide by h. Okay, here's a common place where people make mistakes. They think, okay, this binomial, two terms, x plus h to the n power, must be x to the n plus h to the n, and then they're done. But that's wrong. Think about it in the simplest case, x plus h quantity squared. You have to FOIL x plus h times x plus h. First times first, outside times outside, inside times inside, and last times last. You would get x squared plus 2xh for the outside and inside products, plus h squared. It's not x squared plus h squared. There's an extra term in there. If you were doing x plus h cubed, there's 2 extra terms that you wouldn't necessarily expect, and the coefficients of those terms come from something called Pascal's triangle, which looks like this, where the numbers in any row, like the 4 here, for example, are given by adding the 2 closest numbers in the row above. 4 is 1 plus 3, 6 is 3 plus 3, 4 is 3 plus 1, etc. 1 over here is in effect 1 plus 0. There's 1s along these main diagonals here on the left and the right. And it turns out that these numbers that you see here are the coefficients that you get when you expand. In this case, x plus h squared. It's this row here, 1, 2, 1. This is for the coefficients of x plus h cubed. This is for the coefficients of x plus h to the 4th power, x plus h to the 5th power, etc. The first coefficient is always a 1. The second coefficient, this is the most important one for this video, is always the value of the power. 2nd power, 3rd power, 4th power, 5th power. In this case, that's the n in this general situation. We don't really care about the ones in the middle. The ones on the end here are the powers of h itself. The highest power of h, the coefficient is 1. So we're back to a first 1 times h squared, for example, here. So what does this mean? When we do this limit calculation and expand x plus h to the n power, and it is important that n is 1, 2, 3, 4, 5, 6, 7, etc., a positive integer, we're going to get x to the n power plus, and again, here's the key term, n times x to the n minus 1 power times h. We lower the power of x by 1 and add 1 to the power of h, plus higher order terms that we will not specify the coefficients of. They come from these numbers here that are higher order in terms of higher powers of h. I won't write that, but I'll say that verbally. That's higher powers of h, etc., until the very last term is going to be the highest power of h. I'll go ahead and write that down. That'll just be h to the n because its coefficient is 1. I don't have to write it down, but I will, just for a little bit more specificity there. Don't forget to subtract x to the n power and all divide by h. Now remember, when you do these kinds of problems, you're always hoping, at least with polynomials, that you will be able to cancel all terms that do not involve an h in the top. And in fact, we can. We can do that cancellation, and that's good because then with the terms that are left, we can factor an h out and divide it out with the h in the bottom, which is good because then we can plug in h equals 0. We can't plug in h equals 0 right away because we'd be dividing by 0. If you graph this as a function of h, each graph, well, conceivably could have a vertical asymptote, but in situations like this, we'll have a point missing, a hole in the graph, and that hole can be filled in effectively by dividing out the h. So we go ahead and do that. We cancel the x to the n's. What's left, all these terms in here all have at least one factor of h. It can be factored out. With the first term there, what's left is n times x to the n minus 1 plus, well, let's just say higher order terms, though the order of the h in those higher order terms is one less because we factored out one factor of h. The last factor of h will be h to the n minus 1, all divided by h. I can divide out those h's. Why is that justified? Effectively because in the definition of a limit, it really truly does not matter that the graph has a hole in it. It doesn't matter that the function's undefined at h equals 0. If the limit of the simplified function exists, then the limit of the more complicated function will exist and they will be equal to each other. And then what's left now is a polynomial in h. Think of x as fixed. This is a polynomial in h with higher order terms involving with at least one factor of h in each term. One factor of h in each term. So it's a continuous function of h. You can evaluate the limit by plugging in h equals 0, and all those higher order terms, including the last one, will go to 0. What's left is n times x to the n minus 1 plus a bunch of zeros for the final answer to be n times x to the n minus 1. And we have just derived the power rule that if f of x is x to the n power, at least in the case where n is a positive integer, then its derivative is n times x to the n minus 1. That power rule, I should say without proof, is true, in fact, no matter what n is. If n is negative, a fraction, irrational, it doesn't matter. We can write that in a couple different ways. The derivative with respect to x of x to the n power is n times x to the n minus 1 power, emphasizing we are applying the derivative with respect to x, treat n as fixed. Shorthand, you could just use a prime notation. If you do this, though, it would be understood that x is the variable and n is fixed. This is the power rule. And it's one of the most fundamental rules to know in calculus. In problem 2, the function is a linear function, which is technically not a power function because we have a constant term. You might even argue because we have a coefficient of x that's not 1 here. M and B are constants. Use the definition of the derivative, again, a limit calculation, to compute f prime of x. Maybe you could guess the answer ahead of time, even if you didn't know, thinking about the graph of this function and the fact of what the derivative tells you about tangent lines. Think about that. Here is the limit calculation again. Here is the definition of the derivative. And once again, we're hoping the same kinds of things happen, that we can cancel all terms that do not involve h on the top, factor out an h, divide it out with the 1 on the bottom, and then use continuity at the very end. F of x plus h, go to the formula, replace x with x plus h. Don't forget to use parentheses here. And then subtract f of x. Don't forget to use parentheses here. Many students have trouble with math notation. They look at things like this and it seems kind of meaningless to them. They don't understand how to think about something like this here when f is a function as compared to this here when m is a number. This is f of x plus h. F is a function, not a number. In the formula, you replace x with whatever's inside there. This is m times x plus h, not m of x plus h. M is a number, not a function. We cannot use the distributive property here. This is not f of x plus f of h. We can and do need to use the distributive property here. This is m times x plus m times h. You've got to understand what the symbols represent. That is a big point of difficulty for many people. So yes, now m is a number. Go ahead and use the distributive property here. That's m times x plus m times b. We're going to go ahead and, or excuse me, m times h, excuse me. Go ahead and then add the plus b there. And then subtract, we need to distribute the minus sign through. Effectively, we are adding -1 times that whole thing, so we distribute the -1 through, which effectively means subtract both terms. Once again, as in the first problem, any terms that do not involve h get canceled. mx cancels with minus mx, and b cancels with minus b. You're left with a pretty simple expression. The limit as h goes to 0 of mh divided by h. That's a very simple function of h. Technically, it's a constant function of h that is undefined when h equals 0. Its graph is always equal to m, except there's a point missing when h equals 0. But by dividing it out, we are left with a true constant function that is defined and continuous even at h equals 0. M is a constant. This limit is m itself, and I hope that's what you guessed if you did guess with me ahead of time. Again, this is justified by the fact that, technically speaking, it doesn't matter that this function is undefined at h equals 0. It's irrelevant for the limit. These two expressions, mh over h and m, are equal as long as h is not 0. So if this one has a limit, then this one will also have a limit, and they'll be the same. That's a nice continuous function of h everywhere, including at h equals 0. It's a constant function, and graph is a horizontal line. You always get m. And yes, that does tell you the slope of this linear function, no matter what x is. Now we move on to calculation questions avoiding limits. Number 3, part A. Can the power rule be used to compute the derivative of y equals 1 over x, and if so, compute it? Can the power rule be used to compute that? Remember, I said in the first problem, the power rule was the derivative of x to the n equals n times x to the n minus 1, and I said that was true no matter what fixed value n has, including if n is negative. And you should know from algebra that 1 over x is the same as x to the -1 power. This is a power function. It's not a polynomial. It is a power function with n equal to -1. Therefore, by the power rule, its derivative is n, -1, times x to the n minus 1, -1 minus 1 power. Simplify that a little bit. It's negative x to the -2. That is the answer. You also can write that as -1 over x squared by definition of negative exponents. This is true for all of x where these functions are defined, which is all x except 0. Let's do part B now. Can the power rule be used to compute the derivative of the square root of x? And if so, compute it. So now f of x is the square root of x. Once again, from algebra and pre-calculus, you should know that that's the same as x to the 1/2 power by definition of 1/2 power. It is a power function now. N is 1/2. The derivative of x to the n is n times x to the n minus 1. N is 1/2. N times x to the n minus 1. This simplifies to 1/2 x to the -1/2, which is fine. That is the answer. That can also be written as 1/2 times 1 over x to the 1/2. And then those fractions can be combined because you're multiplying them by multiplying the numerator and denominator. And you also can write x to the 1/2 as square root of x. And this is true for all positive values of x. I'm noticing in the next parts that I've labeled them wrong. This is C. This is D. Part C. Can the power rule and linearity of the derivative, I haven't mentioned what that is yet. I'll talk about it as I talk about this situation, be used to compute the derivative of y equals 1 over x to the 5th plus 1/4. Well, what is linearity of the derivative? Linearity says that the derivative of the sum of two differentiable functions, f of x and g of x, is the sum of their individual derivatives, f prime of x plus g prime of x. This also extends to taking the derivative of 3 or 4 or 5 or 6 functions. It also extends to allowing for constant multiples of functions, and in general what are called linear combinations of functions. When you take the derivative of c, a constant, times a function f of x, the function effectively gets carried along for the ride. You get c times f prime of x. So now we have this function here. Y equals, I'll go ahead and write f of x equals 1 over x to the fifth plus 1/4. You can differentiate each one of these functions individually. 1 over x to the fifth is the same as x to the negative 5. Well, 1/4 is the same as 1/4. That is the same as 1/4 x to the 0 power, you might say, thinking of x to the 0 power equaling 1. Technically speaking, the 0 to the 0 power is undefined, but don't worry about it. And then you have a combination, a sum of two functions. The derivative will be the sum of their individual derivatives. The derivative of x to the negative 5 by the power rule will be negative 5x to the negative 5 minus 1. And the derivative of a constant times a function is that constant times the derivative of the function. If you want, go ahead and write 0 times x to the 0 minus 1. But hey, that's a 0 product there. This is 0. The final answer is negative 5x to the negative 6. I guess I'm answering the yes-no question. We are by computing it right away here. Yes, we can apply the power rule and linearity of the derivative to do this. We get ultimately negative 5 over x to the 6th power. In part D, and this is part E here, in fact, sorry about all this mislabeling, can the power rule and linearity of the derivative be used to compute the derivative of this function? First thing to realize is this function is not the same as that function. They're not the same. Why? You can't break a fraction like this with two terms in the bottom apart like that. Why? Well, if you added these two things by getting a common denominator, it would not equal that. That's one pseudo-justification, you might say. They certainly aren't equal to each other. How do you get a common denominator? The common denominator would be the product of those two things, 4 times x to the fifth. And you would ultimately get 4 plus x to the fifth over 4 times x to the fifth, not equal to this. You can't do that. It's not a power function. It's not a polynomial function. It's not a linear combination of power functions multiplied by coefficients. So the answer for D, this true D here, is no. Power rule and linearity cannot be used to compute it. Finally, we go on to part E. Can the power rule and linearity be used to compute the derivative of y equals 2 to the x? Now the variable is in the exponent. This is an exponential function, not a power function, not a polynomial, not a sum of power functions, not anything like that. No, you cannot use the power rule to differentiate an exponential function. The answer for E is no. Number 4 also involves the power rule and linearity, and it just says find the derivative, so evidently we must be able to do it, of the function f of x equals 3x squared times the 5th root of x plus a fraction, yikes, x to the pi power, weird, plus 10x to the e power all over x cubed. It doesn't look like it's possible, but these rules, as well as algebra facts, are powerful. First, before we try to apply the rules, write both of these things, or the entire thing here, as a linear combination of power functions. The 5th root of x in particular, first of all, is the same by definition of 1/5 power as x to the 1/5. X squared times x to the 1/5, you add the exponents. 2 is the same as 10 over 5. That becomes ultimately 10 over 5 plus 1 over 5 is 11/5 for what this piece simplifies to. Whereas in the previous problem, you cannot split apart fractions where the denominator has a sum of two terms. You can split apart fractions where the numerator has the sum of two terms by definition of fraction addition. This here becomes x to the pi over x cubed, which simplifies by subtracting the exponents to x to the pi minus 3. And then with the next one, well, the 10 gets carried along for the ride. You get 10 times x to the e over x to the third, subtract the exponents, and get x to the e minus 3. This is an alternative way to write the exact same function as long as x is not 0, technically speaking. So we're not dividing by 0. Technically, 5th roots are defined when x is negative. X could be negative in this situation, just not equal to 0. Though irrational exponents, we probably don't want to think about negative values of x there. technically speaking, we probably want to think about just x positive. All right, the 3 is a constant in front of this. It gets carried along for the ride. 11/5 is the n here. You could write the 11/5 as 2.2. 11/5 times x to the n minus 1 is 11/5 minus 1. With this next one, pi minus 3. Yes, pi minus 3 is playing the role of n. Bring it all down. Use parentheses. Subtract 1 from that exponent. Pi minus 3 minus 1 is pi minus 4. And with this next term, carry the 10 along for the ride. Bring down the e minus 3. Subtract 1 from that exponent and it becomes e minus 4. That's the answer. You can simplify a little bit if you like. This is 33/5. 11/5 minus 1 is 11/5 minus 5/5 is 6/5. And everything else can just stay as is. Pi minus 3 in parentheses times x to the pi minus 4 plus 10 times e minus 3 in parentheses times x to the e minus 4. That's the derivative of this function. The function in number 5 is a polynomial, which is a linear combination of power functions where the power is 0 or greater, not negative exponents, not fractional exponents. That's a polynomial function. Part A says find f prime of x. Okay, so we use linearity. Let's be careful. The coefficient here is 2, so I just carry that along. Then apply the power rule to x to the third power. Its derivative is 3 times x to the 3 minus 1 power, 3 times x squared. Then the 4 gets carried along for the ride. 4 times the derivative of x squared. The derivative of x squared is 2 times x to the first power, which I will just write as 2x. Then minus 10 times the derivative of x to the first power, which is 1 times x to the 0 power, which is just 1. And then finally, the derivative of 1 times x to the 0 power is the derivative of a constant. Like we saw before, that derivative is 0. Simplify this. This becomes 6x squared plus 8x minus 10. There is f prime of x. Part B. Find the equation of the tangent line to the graph of f at x equals 1. The tangent line is going to have a slope equal to the derivative value at x equals 1, and it will go through the same point as the original function. So we need the value of the original function at x equals 1. Plug in 1 there, you get 2 plus 4 minus 10 plus 1 is ultimately 7 minus 10 is negative 3. Plug 1 into the derivative to find the slope of the tangent line. Plug in 1 here, gets 6 plus 8 minus 10 is 14 minus 10 is 4. The equation of the tangent line then is y equals, if you want to give the tangent line a name, like L of x or something, that's fine. It's going to be f of 1 plus f prime of 1 times x minus 1. I'm effectively using point slope form there of the equation of a line. F of 1 is negative 3. F prime of 1 is 4. We get this. That is the answer. You certainly can also expand it out. You could write it as y equals, you get 4x. Negative 3 minus 4 is a minus 7. Both of those are fine answers. This one would be in simplified slope-intercept form. This is more in point slope form. The point slope form is easier, though, to do part C. Use the answer from part B to approximate f of 1.1. How does that compare with the true value, and how is this comparison related to the value of f double prime of 1? That seems kind of strange. To approximate f of 1.1, we use the tangent line. We compute L of 1.1. It's again easiest to use this form. That's negative 3 plus 4 times 1.1 minus 1. That's a 0.1. This is a calculation you can do in your head. 4 times 0.1 is 0.4. We get negative 3 plus 0.4. This is negative 2.6. How does that compare with the true value? Is it bigger or smaller? Well, let's compute the true value. F of 1.1, we'll use our calculator here, is 2 times 1.1 cubed plus 4 times 1.1 squared minus 10 times 1.1 plus 1. Use my calculator here. 2 times 1.1 to the third power is 2.662. You can write that down if you like, plus 4 times 1.1 squared minus 10 times 1.1 is minus 11, and then plus 1 gives negative 2.498 for the true value. In other words, the approximation is less than the true value, and a number line, negative 2.6 would be to the left of negative 2.498. It's smaller, less than. You could write this if you like. But then it said, how is this comparison related to the value of f double prime of 1, which gives you the concavity of the original graph at x equals 1 or near x equals 1? Well, we better find f double prime of 1. So that's the second derivative. The second derivative of f of x is the derivative of the first derivative. So I need to differentiate this now. Let's do that derivative pretty quickly. I won't even bother being extra careful like I was up here and carrying those coefficients along like I did. Just do it in my mind here. The derivative of 6x squared, bring down the 2, it would be 6 times 2 times x to the first, 12x to the first, which is just 12x. The derivative of 8x is 8, and the derivative of minus 10 is 0. There is f double prime of x. F double prime of 1 in particular is 12 plus 8 is 20, which is positive. The graph is concave up near x equals 1. F double prime is a continuous function. Everything is nice here. So why is that relevant here? Turns out if you graph f of x in this context, when x is positive, it looks about like this. Over here, it also looks like that, but that's not a big deal. X equals 1 turns out to be right about there. You can check it with your calculator. The graph is certainly concave up there. The tangent line is underneath the graph, and so at 1.1, you can see the approximation given by the tangent line is going to be lower, less than the approximation or the actual value on the function itself. Our last problem is a physics problem about throwing a tomato straight up in the air and not worrying about when it comes down and goes splat on the ground. At a time t seconds after it is thrown up in the air, straight upwards, and then it comes straight back down, a tomato at a height of h equals f of t equals negative 4.9 t squared plus 29.4 t plus 3 meters. The negative 4.9, just for background, is related to the acceleration due to gravity. 29.4 is the initial upward velocity, and 3 is the initial height. Part A says, what is the instantaneous velocity at time 2? We did talk about in a recent video that the derivative, when the original function is the position, or height in this case, gives you the instantaneous velocity. So we need to find f prime of t and then plug in t equals 2. Take the derivative of this. It is a polynomial function. We can use linearity and the power rule as before. Bring down the 2. 2 times negative 4.9 is negative 9.8. Subtract 1 from the exponent. 2 minus 1 is 1. The derivative of 29.4t is just 29.4, and the derivative of 3 is 0. Plug in t equals 2. Evaluate. Don't forget to also include units. Negative 9.8 times 2 is negative 19.6. That's 0.6 there, plus 29.4. This is going to be positive. What will it be? 8.8? Is that correct? Or 9.8? Let's see, yeah, 9.8. 9.8 units of the derivative are units for velocity, meters per second. And that is a positive 9.8 meters per second. The tomato is still going upward at that moment in time. It happened to be exactly 9.8. It could have been different. This tomato goes pretty fast at first, 29.4 meters per second. At time 1, I'm sure the speed, the velocity is more like in the ballpark of 15 to 20 meters per second instead of 9.8 or a multiple of 9.8. That's just a coincidence here that it's the same numerical value as the acceleration due to gravity. B says, what is the instantaneous acceleration at t equals 2? Acceleration is found by taking the second derivative, differentiate the first derivative, you're going to get a constant, negative 9.8, and so therefore f double prime of 2 is also negative 9.8. Units are different though. This is acceleration. This is meters per second, commonly written as meters per second squared, but that's just shorthand. It is more meaningful to think of it as a rate of change of velocity. How fast is that changing in meters per second every second that goes by? Though it's a changing, well, okay, in this case it is a constant acceleration, but in general it could be changing. Yeah, that's the constant acceleration due to gravity near the surface of the Earth. Though I did talk recently in a recent video that actually the acceleration due to gravity is not constant. It's just an approximation near the surface of the Earth. If you go into way up high, like on top of a high mountain, the acceleration due to gravity is actually slightly smaller in magnitude. Part C says, at what time does the tomato reach its maximum height, and how high does the tomato go? Reaching the maximum height, that's the instant at which the velocity is 0. At that moment in time, the instantaneous velocity is 0. It's going up, it's got it coming back down. There's a moment in time where it effectively stops. We need to set the velocity, which is the derivative, equal to 0. There's the formula for the velocity. So negative 9.8 t plus 29.4 equals 0. Solve for t. 9.8 t will be 29.4, and so t will be 29.4 divided by 9.8, and that will be 3. I made it nice that way. That'll be in seconds. T equals 3 seconds is when, at what time does the tomato reach its maximum height. The actual maximum height itself needs to take that value of t and plug it into the original function. So the max height is ultimately f of 3. So do negative 4.9 times 3 squared plus 29.4 times 3 plus 3. 3 squared is 9. 9 times 4.9 is 44.1. This is negative 44.1. 29.4 times 3 is 88.2. These combine to give you positive 44.1. Add 3. That looks like the final answer for the maximum height is 47.1. That would be in meters. There you go. There's the maximum height. Thanks for watching.